Okay, welcome to the 6th video that I'm recording on how to verify trig identities. This is part 3 of 3 of my second 3-part series. In this 3-part series, we're doing slightly more advanced trig identities. They're not like the hardest things in the world. Over the next couple months or years, I might continue to record videos on even harder ones. But if this is like the first video that you're watching on identities, I would definitely stop right now and go back to the previous ones, starting with the simpler ones in my first 3-part series. In this one, I'm going to go through 4 more advanced verifications. We're going to use some cofunctions, some odd evens, some double angles, and of course we're going to continue to use our reciprocals, our Pythagoreans, and a ton of algebra. So let's go ahead and get started. We have cotangent of pi over 2 minus x, all right, times cosecant is equal to secant. Of course, the right-hand side is easier. We're going to keep that as is and change the left. And to do this, we're going to start with our cofunction identity. And cofunctions are all about, sort of like, if you think of it like, like a complement. When we talk about complementary angles, we're talking about angles that add up to 90 degrees. Well, the easiest example is to go back to, like the sine of 30 degrees is equal to the cosine of what? Well, that was, of course, 60 degrees, right? Sine and cosine are called cofunctions because the sine of one angle is equal to the cosine of the other angle's complement. In other words, 30 plus 60 is 90. And I can do that with any angle. If I want to take, the sine of 7 degrees and ask the question is equal to the cosine of what? Well, I know that that's 83 degrees. All I'm doing in my head is 90 minus 7. Well, the same thing works for radians. If I take the sine of an angle, let's say, I don't know, pi over 4. That's not a great example, but let's take pi over 3. Is equal to the cosine of what angle in radians? Well, all I need to do is think about what's 90 degrees minus that. Well, 90 degrees in radian form is pi over 2 minus that. Well, that's going to be, let's see, 3 pi over 6 minus 2 pi over 6. I want common denominators. That's, of course, going to be pi over 6. All right, and that makes sense. Pi over 3 is 60 degrees, pi over 6 is 30 degrees. So if we're thinking in terms of radians or degrees, we should be able to get the same types of answers. So in any event, sine and cosine are cofunctions. Well, guess what? Cotangent and tangent are also cofunctions. So if I think about the cotangent of pi over 2 minus some angle, well, that's just equal to the tangent of that angle right here, times cosecant of x. All right, so I just made a really simple substitution here using cofunctions. And now, sorry, there's the bell again. And now I'm just going to convert things to sines and cosines. Sine over cosine times 1 over sine. Now the sines cancel. All right, sine on top, sine on bottom. I get 1 over cosine x equals secant x. Well, that's the reciprocal identity, and I'm done. All right, so not a very long verification, but it does involve, cofunction identity, which is something that we haven't looked at in any of my previous 5 videos. So let's continue. All right, next up I have a verification that's going to require odd and even functions, right? So if we think about odd and even identities, right, when we say odd or even, we're talking about functions that have symmetry. An odd function such as tangent has symmetry across the origin. Sine also has symmetry across the origin. Whereas even functions such as cosine have symmetry over the y-axis. All right? So when we have an odd function, the sine of negative x, well, the sine of negative x is equal to the sine of x. But there's a minus sign in front of it. Alright, so that's what we're talking about when we say odd, right? If you think about on a graph, or if we graph sine, and we think about the sine of, let's say, the sine of pi over 2. Alright, the sine of pi over 2 is 1. Well, if we go over here to, well, that's not a very good drawing, but if we go over here to negative pi over 2, I'll draw it in green, negative pi over 2 is negative 1. Right? So if we go and replace x with pi over 2, we can see that it works. Right? The sine of negative pi over 2 is negative 1, and the sine of pi over 2 is 1 with a negative in front. All right, that's what we call an odd trig function. And it turns out that sine is odd, its reciprocal, cosecant, is also odd, and as I just showed you, tangent is odd as well, which means cotangent is too. So in general, if you want to write these down, sine of negative x is equal to negative sine x, cosecant of negative x is equal to negative cosecant x, tangent of negative x is equal to negative tangent of x, cotangent of negative x is equal to negative cotangent of x. These are odd functions. The even function, of course, is cosine. Cosine is an even function, which means that if we were to graph it, it has y-axis symmetry. And that's a terrible drawing, but you get my idea. So in other words, when we take and examine, let's examine the cosine of pi. The cosine of pi is negative 1. Well, if we go backwards now and draw another cycle, the cosine of negative pi is also negative 1. So the cosine of negative pi is equal to the cosine of pi. All right, that's called an even function when that works that way. And guess what? If cosine has that even quality to it, then secant does too. Alright, so these are called odd functions up here, odd, and these are called even functions down here. And this is the first time, I think this is the first time we're using odd and even. So let me erase these and we'll actually make some substitutions here. The numerator is cosecant of negative x. Well, that's equal to negative cosecant of x. The denominator is secant of negative x. Well, that's equal to secant of x. Can I get that to equal negative cotangent of x? Well, let's turn these into sines and cosines. So I've got negative 1 over sine x, all divided by 1 over cosine x. When we divide by fractions, it's sometimes helpful to write them horizontally. So let's divide by this fraction. When we divide by fractions, it's the same as multiplying by the reciprocal. So keep this, switch to multiplication, and flip it over. The way I kind of say that to my students is when you divide fractions, you keep it, you switch it, and you flip it. Keep it, switch it, flip it. So now we just multiply negative cosine x over sine x. Does that equal negative cotangent x? Yeah. Definition of cotangent is cosine over sine. So this is negative cotangent x is equal to negative cotangent x. That works. Let's move on. This next one, you can see that we have two fractions that we're trying to subtract. We need to set that whole left side and get it equal to negative 2 tangent x. So when we add or subtract fractions, we're looking for common denominators. All right, so I'll very briefly go through the same example that I did last time in video number 2. If you're asked to subtract these fractions, you need to find their common denominators, and the easiest way to do that is to just multiply the denominators together. 7 times 5 is 35. To get 5 to be 35, I multiplied it by 7, so let's multiply 7 times 3. whatever I do to the bottom, I need to do to the top. 5 times 2 is 10. 21 minus 10 is 11, and keep the denominator the same. So that's how we change our denominators, right? That's basic algebra, pre-algebra stuff. And what I want to do is apply that same concept here. Right? So my numerator is going to change in both fractions, but my denominator, I'm just going to simply multiply them together. Right? Just like we did here, 5 times 7. Well, I'll just multiply these two together. Just bump them up next to each other. Now my numerator right here is going to get multiplied by this denominator. So I'm not going to distribute them. I'm going to write them next to each other, minus, and then this one goes up and multiplies by that. Okay, and from here, let's recognize that both of these terms in the top have a common factor, or a common term. They both have a cosine in them. So let's take that out. Let's get rid of this. Let's take a cosine out of both of those blue terms. When I remove a cosine from both of these blue terms, that leaves me with 1 plus sine x minus 1 minus sine x. Be careful with your minuses and your parentheses. All I'm doing is I'm taking out a cosine from both blue terms. When I say take out, of course, we're talking about division. Okay? And again, this right here is kind of tricky. You got to make sure you write down that minus sign, but then there's this thing in parentheses. So be careful with that. Now let's take care of that parenthesis that's going to distribute into both terms after it. So 1 plus sine x minus 1 plus sine x. My denominator doesn't change. I'm just going to keep that like that for a second. I don't want to do too many steps at once. In my numerator, positive 1 minus 1 cancel out. So I have cosine x parentheses sine x plus sine x. Well, I'll rewrite that actually as 2 sine x. 2 sine x. Be careful not to say that it's sine squared x. That's not true. So that's equal to 2 tangent x. I'm just going to rewrite my denominator. I think at this point it might be a good idea to FOIL the denominator. You can see that if you FOIL these, it's going to turn into, let's see, first times first, outside is sine x, inside is negative sine x, the last is negative sine squared x. So these cancel out, the outside and the inside. So what I'll do is I'll just write it as 1 minus sine squared x. 1 minus sine squared x is my denominator. My numerator is cosine x times 2 sine of x. I don't really need to keep writing that those parentheses anymore. I can just write it just like that. All right, 1 minus sine squared x, well, that's Pythagorean identity. That's cosine squared x. So if I rewrite my numerator and change my denominator to that, I can see that I have a nice cancellation. Cosine, there's one cosine up here, and there are 2 of them down here. So let's just cancel out this one and one of these. So I get 2 sine x over cosine x. And this is really nice. What is sine over cosine? Sine over cosine is defined as tangent. So I have 2 times sine over cosine. Well, sine over cosine is tangent, so I'm not even going to write that. I'm going to just turn that right into tangent, and I'm going to see that I'm done. All right, last one. Pause it, give it a shot, see if you can get it. And when you finish, just press play, see if you got the right answer. What I'm going to do is keep my right-hand side the same. There's not really too much I can do with that right now. And I'm just going to FOIL this side. Right? When I multiply a binomial times itself, I get, let's see, first times first, sine squared alpha, plus, let's see, outside is going to be sine alpha cosine alpha. Inside, I need to move this over a little bit. Inside is the same thing. And the last times the last is cosine squared alpha. From here, sine squared plus cosine squared, that's 1. And these two things added together is 2 sine alpha cosine alpha. Alright, so this one is actually not that long. The only thing is it requires at this point for you to know that this whole thing, you need to use a double angle identity. Alright, if you didn't really know that, this problem's kind of tricky, but that whole thing by definition is exactly what is on the right hand side. Alright, so hopefully you have your formula sheet handy and you can always sort of refer back to these things, but when we say double angle, we're talking about literally it's 2 times an angle. So 1 plus 2 times this is equal to this whole thing by definition. So it works out, we're finished. And that takes care of part 3 of my more advanced, slightly more advanced trig identity series. So hope you enjoyed it. Right, that concludes. This is my 6th video on verifying trig identities. So hopefully you're starting to get better at these things. As I say all the time, just continue to practice like crazy. These take a lot of effort, a lot of practice, but you're going to notice that you're going to get better at them as the more you do them. So thanks for watching, and I will see you in the next video.